you so much for joining this video. Here are today's learning objectives. So we're first going to know that a Bronstead-Lowry acid is a proton donor and a Bronstead-Lowry base is a proton acceptor. We're then going to know that acid-base reactions involve the transfer of protons, and then we're going to be able to identify Bronstead-Lowry conjugate acid-base pairs. First, we're going to go through some definitions. So a Bronstead-Lowry acid is a proton donor and a Bronstead-Lowry base is a proton acceptor. So for example, if we had hydrochloric acid, the gas, being dissolved into water to form the H3O plus ion and a Cl minus ion, then that means that this hydrochloric acid, this is acting as the proton donor, and the water is acting as the proton acceptor. And so here we have the acid and the water is acting as the base. And the third thing to know is that acid-base equilibria involve the transfer of protons. So now we're going to talk more about acid-base equilibria. So when an acid reacts with a base, an equilibria is actually set up, and we're going to look at why this is the case. So when a molecule HA protonates a water molecule, so HA is just the general form of an acid, it acts as an acid. So in this first equation, we have HA acting as the acid and H2O acting as the base, because HA is donating that H plus, the proton, and H2O is accepting it. And so we form H3O plus and A minus. The A minus and H3O plus can then collide again and a proton can be transferred again. And so in this case, we have that A minus is the base and H3O plus is acting as the acid. And so an equilibrium is set up where we have HA plus H2O on one side and H3O plus plus A minus on the other side. And we say, we call this kind of pairing conjugate pairing. And basically the conjugate base of HA is A minus. So here we have, let's call it acid 1, and H2O is base 1. Then we have acid 2 and base 2. So the conjugate base of HA is this A minus, and the conjugate base of H2O plus is this H2O. And the conjugate acid of A minus is HA, and the conjugate acid of H2O is H3O plus. So that's the opposite way around. Water is actually quite an interesting example because it can act as an acid or a base. So for example, if we had water and HCl, that would form this H3O plus ion and Cl minus. Now this H3O plus ion is actually called the hydroxonium ion, and it's equivalent to a H plus. So this 3-line symbol means equivalent. And so in this case, water is acting as the acid, so in this case, water is acting as the base, whilst HCl is acting as the acid. However, if you add water with ammonia, NH3, we then get this NH4 ammonium ion and a hydroxide ion. And in this case, the water acts as the acid, as it's giving away the proton to the ammonia. So then the ammonia is the base. So if we were to look at a proton transfer equilibria example, we could have sulfuric acid added with water, and this would form HSO4 minus the ion and H3O plus, and sulfuric acid would be acting as the acid, and water would be acting as the base, as it's accepting that proton. And actually what we find is that this HSO4 minus ion then acts as an acid again when you add more water. So you'd get HSO4 minus plus water, and this would act as the acid and water as the base again. And you would form SO4 2 minus the ion and this hydroxonium ion again. And so this would be the base and this would be the acid. And so overall, the proton transfer equilibria for sulfuric acid would be, so overall you would get H2SO4 plus 2 waters would form this SO4 2 minus ion and 2 of these hydroxonium ions, because basically the HSO4 minus is kind of the intermediate, so it's been used up in the second reaction. And so this is the overall equation. Now we're going to look at some questions. So for question 1, identify the acids and bases on the left-hand side of each of the following equations. So now we need to remember the definitions of Bronstead-Lowry acid and Bronstead-Lowry base. So a Bronstead-Lowry acid is a proton donor and a Bronstead-Lowry base is a proton acceptor. And so we see this NH4 is losing a proton. And so it must be the acid, because it's donating the proton to the water. And so water acts as the base. And then for B, we have water and this H2PO4 minus ion. And we see that H2PO4 minus is losing a H plus. And so that acts as the acid. And the H plus is going to the water to form the hydroxonium ion. So H2O is acting as the base. And then for the last reaction, we have NH4 plus and NH2 minus, and it forms 2 NH3 molecules. And so the first, the NH4 plus, it's losing a H plus, so that's acting as the acid. And the H plus is going to the NH2 minus to form ammonia, so NH2 minus is acting as the base. Before I move on to number 2, feel free to click off the video and try it for yourself first. So write equations for the donation of 1 proton to 1 molecule of water by each of the following acids. So for A, we have nitric acid, and we're reacting it with water. And this should form, in an equilibrium, it should form NO3 minus and H3O plus, the hydroxonium ion. And then for B, we have sulfuric acid, and this reacts with water. And this forms the HSO4 minus ion plus H3O plus. Because what we're doing is we're donating one of the protons from the acid to the water. And so the hydroxonium ion is always formed. And then for C, we have phosphoric acid added with water. And this forms H2PO4 minus plus H3O plus. And the acids always form 1 minus ions because we're losing 1 H plus. So we're losing one of the plus charges, one of the positive charges. That makes it neutral. And then for D, we have H2CO3 plus water, and that goes to form HCO3 minus plus HO3 plus.